Today we will look at some problems about homework 6. For the first problem, we need to determine the water rise, H. First, we sketch a string line and select 2 points along it. So this is string line, and we select 2 points. This is point A, this is point B. And we assume the depth below the water surface is D. So yes, this is D. And we apply Bernoulli equation between A and B. We have ZA plus PA over gamma plus the VA square over 2G equals CB plus PB over gamma plus VB square over 2G. And we know ZA equals CB. And the VB should be equal to 0, since the point B is stagnation point. And then the Bernoulli equation can reduce to PA over gamma plus VA square over 2G equals the PB over gamma. And then we apply apply this 2G hydrostatic equation. So we have that the PA should be equal to the gamma times D, and the PB should be equal to the gamma times H plus D. And then we have that D plus VA square over 2G should be equal to the H plus D. And we can determine that H should be equal to the VA square over 2G. And we know VA is 6.6 meters per second, and the G is 9.81 meters per second square. So we can determine that the H should be equal to the 2.22 meters. Actually, this problem is very similar to an example on page 130 on your textbook. You can double check with it. So we finished this problem. For the second problem, we need to determine which of the flowing statements are valid. Let's look at point C first. We know when the string lines are straight and parallel, the barometric pressure will be constant along a line that is normal to a string line. And we'll show on the bottom of the section D is stated. So this is stated. And now we know that PC plus 0 should be equal to the PD plus gamma times D. The PD is the pressure at the water surface, and the D is the depth of water. And actually, this is also equal to the PZ. Actually, this is barometric pressure. And so we can get that the PC should be equal to the PD plus the gamma D equal to the PZ. This is for the point C. And then let's look at the point A and the B together. We know when the string lines are curved and the barometric pressure will increase along a line that is normal to the string line. And the direction of the increase in pressure will be outward from the center of curvature of the string lines. So we can get that for the point B. The PB plus 0 should be greater than the PD plus the gamma D equal to PZ. So we can get that the PB should be greater than the PD plus the gamma D. And for point A, we can get that the PA plus 0 should be less than the PD plus the gamma D equal to PZ. So we can get that the PA should be less than the PD plus the gamma D. So PC, PB, and PA. And then combine these three equations, we can get that the PB should be greater than PC, should be greater than the PA. So the answer is, the solution is B. For the third problem, we need to determine the flow is rotational flow or not. We know a rotational flow requires that the partial derivative of u with respect to y should be equal to the partial derivative of v with respect to x. And from problem, we know that the partial derivative of u with respect to y should be equal to 0 minus cx times 2y divided by x squared plus y squared. So that is equals 2 minus 2 cxy divided by x squared plus y squared. And the partial derivative of v with respect to x should be equal to 0 minus cy times 2x divided by x squared plus y squared. So we can see also equals to the minus 2c times x times y divided by the x squared plus y squared. We can see this one equals this one. So we can determine that this flow is rotational flow. For the first problem, we need to determine the discharge in cubic feet per second and in gallons per minute. And we know the Q should be equal to the V times A. From the problem, we know the velocity V should be equal to the 10 feet per second. And we know the A should be equal to pi divided by 4 times d squared. And we know D equals 21 inch equals 1.75 feet. So we can determine that the Q should be equal to 10 feet per second times pi divided by 4 times 1.75 feet square. So we can determine that the Q should be equal to the 24.1 cubic feet per second. And we know the 1 cubic feet per second equals 449 gallons per minute. So we can get that also the Q also equals to 24.1 cubic feet per second times 449 gallons per minute per cubic feet per second. So also equals to 0.8249 gallon per minute. So we finish this problem. For the fifth problem, we also need to determine the discharge in the channel. And from the problem, we know this is a rectangular channel, and this rectangular channel has a 30-degree incline, and we know the vertical depth equals 1 meters. So we can determine the water depth D. The water depth D should be equal to the 1 meters times cosine 30 degree. So D should be equal to 0.866 meters. And from this figure, we know the U, the velocity, equals y to the power of 1/3 meters per second. And we know the velocity is not constant over the area. So we need to apply the integral form of the flow rate equation. So the Q should be equal to the integral of U times the dA. And we know this is a rectangular channel, so the differential area of dA should be equal to the W times dy. And in this problem, we know the width of the rectangular channel is 1.2 meters. So the W equals 1.2. So can determine that the dA should be equal to the 1.2 times dy. And we also know the U equals y to the power of 1/3. So we can find that the Q should be equal to the integral of y to the power of 1/3 times 1.2 times dy from 0 to the 0.866, and equals 1.2 times integral of y to the power of 1/3 times dy from 0 to the 0.866. So equals 1.2 times 3/4 times y to the power of 4/3 from 0 to 0.866. So we can determine that the Q should be equal to the 0.743 cubic meters per second. We finished this problem. For the last problem, we also need to determine the discharge in cubic meters per second. And the definition of discharge is a volume divided by the time. So the Q should be equal to the volume divided by the delta T. And we know the volume can be equal to the weight divided by the gamma. So we can get that the Q should be equal to the weight divided by the gamma times delta T. And from the problem, weight W should be equal to the 80,000 Newton. And we know the water temperature T is 20 degrees Celsius. So we can determine that the gamma should be equal to the 90 Newton per cubic meters. And we also know delta T is 1 minute equals 16 seconds. So now we can find that the Q, the discharge, should be equal to the 80,000 Newton divided by the 90 Newton per cubic meter times 60 seconds. So the Q should be equal to the 0.136 cubic meters per second. So we finished this problem.